Okay, it's working. Okay, so exam one, you did a pretty good job. You can see here the mean for the, now I've separated this into the two different, you'll notice that there's two different versions of the test, and you can tell which version you have by looking at the top left corner, and you'll see exam one spades or clubs. If you're familiar with those symbols, if you aren't, you can ask a friend. It's not a big deal. I mean, I've had students who have never seen a deck of cards. That's just a cultural thing. So, but I just, anyway. So club spades, so the mean was 81 for clubs and 89 for spades. Median, 83 for clubs and 92 for spades. And you can see here the distribution for those two tests papers. In box plots, I've got the box plots on their sides so that you could compare them, clubs and spades. Now, an obvious question that you might have for me is, was the clubs test, was that harder, a harder exam than the spades test? For some reason, the grades are lower for the clubs than they are for the spades. This one person, I don't know who that was, so if I'm not calling you out, I'm just saying that there's an outlier down here, to be honest, and that pulled the mean down, but still the median doesn't get moved, doesn't get affected by outliers, and so the median is still lower than the median for the spades version of the test. This is an important question that I always worry about when I give two versions of a test, and so I do statistics in order to figure out whether or not this test was harder than this one. We'll talk about that more, though, after fall break. I can assure you, though, that these tests were the same, basically the same difficulty level. You can even compare with your friends, and you'll see the difference. There is no difference, really. The difference is only cosmetic, let's say. So you'll just as an example, if you compare the two, at the first one, number one, the very first question is what is the sample, and for number two, or the second version of the test, it's what is the population. So I just basically jumbled the questions around. And then I made some slight differences in the numbers you had in the calculations, but it wasn't enough to make it, you can compare. If you do have complaints though, since this is our first exam, and probably the first exam you've had with me, you should know that I am susceptible to argument. If you have a complaint, I'm happy to hear your cries for mercy. And I will listen to your argument, and I will probably tell you that I'm right. But I will be sympathetic as I listen to you begging for a point or two here or there. But no, seriously though, I've had students come up to me afterwards and say, Dr. Noonan, I notice here, oh sorry, this is someone's ex, no, this is my key. Oh, I put a sticker on my key. Anyway, I got a sticker. But anyway, I've had students come up to me afterwards and say, Dr. Noonan, it says here this problem's worth 10 points and you took off 20 points. I was like, oh, I made a mistake. Yeah, so that sort of thing happens. Also, sometimes problems are ambiguous the way they're written. I hope not, but so feel free to come up and complain if necessary, but I think it was pretty fair. So stick around afterwards if you want to mine for points on your exam. Otherwise, hang on to this. You can look it over, and if there's anything that you're not sure about, make an appointment with me, come see me. I'm happy to talk to you and help you figure out where you went astray. Let's say if you didn't do well, like if you're down here somewhere and you want to be up there somewhere, we can make it happen. Seriously, if you're down in this quartile, you can get up to the first quartile. I've had students do that from test 1 to test 2. Just come see me. We will work it out. It'll take some effort, though, just to warn you. Okay, moving on. What else we got? Oh, yeah, measures of variation. Yeah, you guys all have or I hope I have enough here. Does everyone have a little bell curve? You got a bell curve here? You don't have a bell curve? I didn't give you a bell curve. Oh, my God. Wait, I gave someone the bell curve. Now everyone's got a bell curve. Yeah, we'll use this in a bit. It's just a little tool that we're going to use to help. I don't know if it's helpful. It may not be helpful. If it isn't, you can throw it away. There it is. Oh, and before we get started, I have yet another installment of statistics you can use. Now this one, in order to keep you focused, I thought I'd ask you for your opinion first, and then I'll show you the statistical study that at least gives evidence for this particular thing later on. So at the end, don't worry, before the end, I will show you the answer to this question. So women, here's the question for you. When should you approach that guy you're interested in to maximize the chances of catching his eye? So is it just before he enters the cafeteria? Or is it just before he enters the chapel? Or is it just after he leaves the gym? Or maybe it's just after he leaves his statistics class. You know, that's the time he'd be the most susceptible to your wiles. Or perhaps it's just before he retires to his room in the evening, you know, when he's kind of tired, his guard is down. So when is the best time to approach that guy you've been eyeing, you know, to make the move, if you will? So take a guess, and guys, maybe you could also guess, when are you most susceptible? So take a minute, take a guess. Like I said, I'll have the answer at the end. Now, guys, I know you think that I'm giving the women some sort of a, you know, like special secret information here to help them out. So I want to make sure that I help you out too. So I've got a second question from a different study. Men, guys, so what part of the body should you emphasize while dancing in order to catch, you know, best impress the ladies? So should you be, you know, shaking your butt more? Or is it your right knee? Or maybe it's your left elbow or your head, or maybe your left foot. So take a guess, and then you've got women, you could also take a guess as to which one you would be most impressed with, to see some guy shaking, you know, doing this while they're, I don't know. I don't dance, just so you know, it'd be scary, yeah. My wife says I dance like a robot, which, you know, I'm like the white guy dance, literally. I'm a white guy, come on. Okay, so there it is, there's the two. At the end, I will show you the answer to both of these. Statistically supported evidence. Okay, onward though. So let's see, range. I don't like this one. Let's move on. Okay, give me a sec. I just realized I need to fix something here. See, I'm so scattered today. Why is this? Hold on a minute. Let me fix this. Sorry, something is awry. Let's fix this. Okay, it's fixed. Okay, so we can talk about range. So what we're going to be doing today is we're going to be talking about how spread out data is. We're going to use these normal curves to estimate how much data is in various ranges. But first of all, the range. The range is just, we've talked about this before a little bit, and it was on your test, so it's not a big deal. And that's the highest to the lowest. And so you might have this question, how many miles did your instructor ride last year? And I made this up a few years back, and this is not true. Not from this 12,000 miles? I don't think so. Yeah, no, I've never been 12,000 miles a year for my bike. But anyway, so a range would be just the biggest to the smallest. So some instructors might have 0 for their number of miles they rode, and some people might have a lot. Age, you can have a range as well, where you have you know, the highest to the lowest. I don't know where these numbers came from. I don't really care, to be honest. So now, why is this not showing up properly? I don't know. That's terrible. Okay, so let's see if I can. No, they're terrible. Hold on a sec. I'll just put them up on the screen using this. So we're going to use, we've already talked about the quartiles as a way of measuring how spread out things are. Another way is using what's called the variance. Now, don't get all bent out of shape about these formulas. I know they're scary. I'm just going to explain them to you briefly. Just briefly, not to worry. I'm not going to make it hard. And to be honest, I'm not going to make you calculate this stuff by hand. You're going to do this on Excel. We're going to do it on Friday, so don't worry. So I'm just going to make these bigger so you can see them. And since this is on the computer now and not on my iPad, I have to do it that way. Okay, so let me just explain what this is. So you know what this symbol means here. So let me orient you to these things. So this X bar, that's the average, right? It's the mean. In fact, let's do this. Let's do this for a particular measurement. Give me a sec here. I'll grab this. I'll just do this because I can't trust PowerPoint at this point. Okay, so let's talk about heights. Height. Okay, so how tall are you in inches? Do you know how tall you are in inches? If you don't, take a guess. Write it down. I'm going to guess 73 inches for myself, but you can put your number down, whatever it is. 73 inches, by the way, is 6'1". I used to be 6'1", but I've gotten older and I've shrunk a little bit, but I still say I'm 6'1". It says on my license I'm 6'1". But anyway, so there's height. Your height, you got it in inches? Now what I want you to do is I want you to compare that with the average height. So guys, men, average height is 69 inches. So compare that with the average height. Are you taller than the average dude? Are you shorter than the average dude? Women, average height is 64 inches. How about you? Are you taller or are you shorter than the average? Now here's the thing, is we can take all of our comparisons, like I could take my comparison, I am 4 inches taller than the average dude, and everyone else's comparisons, you might be 2 inches taller, you might be 3 inches shorter, whatever, but because this is an average, necessarily some of us will be taller and some of us will be shorter than the average. That's just the way it works. So we could take all of our comparisons and then sort of average them together, couldn't we? And that's what the variance is. It's sort of an average of everyone's differences. So here's what I'd like you to do, is to take your height and subtract the average height. So the way I'm going to write this is this. I'll write x minus x bar. So let me label these. Here's x bar. So my x minus x bar is 4, which means I'm 4 inches above average. Your x minus x bar is going to be something different. Some of you have a negative x minus x bar, and that shouldn't be a negative about you. It just means that you're shorter than average. Maybe I should have picked something that wasn't, I don't know. People feel funny about height. But anyway, so there it is. So now here's what we could do, is we could average together all of our differences. So I could take this, so I'm 4, someone else might be -2, someone else might be 6, some really tall dude. Someone else might be -5, someone really short. Anyway, I could take all of those and average them together. But before I do that, you'll notice that because some of us are positive, above average, some of us are negative, below average, we're going to cancel each other out. And essentially, if you do this with a real set of data, you end up getting 0 when you add up all of the pluses and minuses. It balances out. And so before we go and average these together, what I'm going to do is I'm going to square this. So square it, meaning multiply it by itself. And when you multiply a negative number by itself, it becomes positive. And then this is 36, and this is 25. And then I'll average those together. That's the variance. The variance is just the average of the squared difference from the mean. So it looks like a scary formula, but it's really not that bad. All this means is that what I'm going to do, and I'll get to that in a minute, is I'm going to take the difference between each of you and the average, square that, and then, okay, I guess we have to deal with this as well. We'll talk about that in a minute. But you're basically adding them up and dividing by the number of numbers. And I know there's a -1 here. That's another issue that we'll have to deal with. But that's generally the idea here. This, whenever you see Greek letters, it means you're dealing with a population. So this is the entire population average. And these are all the people. And this would be the population variance. So these are variances. Sample variance is this one with Roman letters or Latin characters, and the Greek letters are the population variance. Okay, so that's sort of just a setup. On Friday, we're going to do this on Excel. Have I told you got to bring your computer Friday? Okay, if I didn't, just remember, Computer Friday. What time is it? We got 8:10. We're good. Okay, moving on. Let's see what we have here. Yeah, on the computer, we'll deal with that. Okay, so when we talk about standard deviation, you've probably heard this term, standard deviation. Standard deviation is just the square root of the variance. So you take the variance, do the square root, and you come up with the standard deviation. So that's all that is. And once again, we'll do this on Excel. So this is basically just the average square difference. By the way, the reason for the n-1 is because we're using the sample to estimate how variable the population is, and you subtract 1 to sort of hedge your bets. What that does is when you put a smaller number in the denominator, it makes the entire thing bigger. So it kind of says, okay, I'm not sure that I've got the right number, so I'd like to just make it a little bit bigger to account for the fact that I'm using a sample to estimate a population. So that's all that -1 business is. But the important thing here is that you're averaging together all of the squared differences. So we take all of our differences, square them, average them together. Okay, so that we're going to do on Excel on Friday as well. Bring your computers, don't forget. Okay, so we've already done height. Let's see. Do we really want to do this? Sure, why not? So let's actually do this for real. So give me a sec here. And so we're going to do this once. Only once will we do it by hand because it's so painful. And then we'll do it using the computer on Friday. That's supposed to be an X bar. So the first thing I need to know is I need to know the average. So I don't know what this stuff is. I've got a bunch of numbers. How many numbers? 6 numbers. I've got 6 numbers, and I need to know the average. So let's go over here to computation land, and I need to know the average. Take a minute. See if you can average. I know you can. Average those numbers together. And make sure you write down the total, because I want to know what the total is, too, just for fun. Oh, no, go back. Total. Okay. I'll fire up the randomizer. Random people. All right, let's do this. Bailey, you know what the sum of those numbers, what's the total of all those numbers?
61.
What? What? Wait, are there 2 Baileys? Oh, there's a Haley! Oh, hilarious. I'm sorry. I need to enunciate. That's my fault. My fault. Okay, so Bailey, what was it?
60.
60? Okay, I believe you. 60. And Haley, what do you get when you divide that by 6?
When you divide it by what?
6.
10.
It is 10. That's the average, isn't it? So good. 60 divided by 6 is 10. That's the average. Look at that. I picked a number that's going to be really easy. Isn't that nice? Now, here's the next thing you're going to have to do. You're going to have to take the difference between each of these numbers and the average. Take a minute and do that. Okay, I know you're still working your way through this, but I need to get them written down here. So Carter, could you help me out with the first 2? What's the difference between 2 and 10? So what we're doing here is we're doing 2 minus 10.
8.
Yeah, -8, right? Because the 10 is bigger than the 2. And what about the 5? What do you get when you subtract 10 from 5?
-5.
Very good. All right, onward. We'll go to the next person. What about Aubrey? What about the difference between 10 and 10?
0.
Oh, yeah, it's 0. What about 11?
1.
All right, we're moving now. All right, oh, Haley, I already picked on you, so we're going to just skip on. Gabrielle, what about 14?
4.
4, very good. And 18?
8.
Yeah, see, so we're just doing the difference between each of those numbers and 10. We're doing great. Now we have to square these. I'll bet you can do it in your head, but if you need your calculator, understand. I had a math major once in my office, and I said, we're working through a problem. It's like, okay, so the answer is 2 times 3. And he pulled out his calculator, and it's like 2 times 3. I know, it's embarrassing, but I think I make people nervous whenever I'm sitting right next to them doing math. So if you need your calculator, that's fine. Let's go ahead and get some perfect squares here. Kylie, do you know what -8 squared is? It is 64, and it's positive, isn't it? That's so great. All right, onward. Where am I? I think I'm sick of this. I'll just start going down rows here. How about Calvin? What's -5 squared?
25.
All right, very nice. Alana, what about 0 squared?
0.
Very good. So notice I'm just taking that number and squaring it. All right, let's see. What about Briar, right? Briar? All right, see, it's good for me to practice. What's 1 squared? All right, very good. Carter, wait, I already picked on you. Mason, I didn't pick on you. What about 4 squared? Beautiful. And then 8 squared. Diego? 64. Now we can add those up. Let's get the total. So the formula is this. X minus x bar, quantity squared. And then we're going to divide by, it depends on if this is a population or a sample. Let's wait and see what this total is before I decide if I'm going to divide by 5 or 6. We'll explain in a minute. But add those things up. I'll do the same up here. 16, 16, 90. Let's see, I'll verify. I did it in my head, but I don't trust my mental calculator. Allie, what did you get for the total of all that?
170.
Okay, phew. I always worry this early in the morning whether or not my calculator in my head is going to work okay. Okay, so since that is divisible by 5, I think I'll do n minus 1, just so that it'll not come out nicely. So the difference is, here, I'll take that. I'll tell you the answer to how to impress the ladies later. I know he wants to know. Okay. So anyway, so now divide by, the difference is that if this were a population, which it probably isn't, there's only 6 members, but if it were an entire population, you divide by n, and when it's a sample, you divide by n plus 1, which makes the entire standard deviation. It's an estimate of the standard deviation, and so we just make it a little bit bigger to hedge our bets, so to speak. So who do we have to do this for me? You've already done something for me. You've already done something for me. AJ hasn't yet. AJ, what do you got when you do 170 divided by 5?
34.
34? Yeah, that sounds right. Okay, so 34. That's going to be the variance. The variance is 34. Now the standard deviation, so here, there's the variance is sometimes represented as squared. Standard deviation is just the square root of this. You have it on your calculators. Almost all of my calculators have a square root button. There's only one that doesn't. Let me find it. I don't see it. Did someone steal it? Someone must have stolen it. No, here it is. Here it is. There's the, oh no, that does have a square root button. I'm surprised. It's so junky, but it still has a square root button. So it's the thing that looks like, I don't know, a little check mark almost. But let's see, who gets to do the square root? You've already done something. Oh, I should just stop this. Amy, I don't know if you've done something, but you know what the square root of 34 is, right? It is 5 point something. Okay, I'll just guess 5.9. Good enough? Sure, yeah, 5.9. Okay, now that we've done all this work, that's the only time I'm going to make you do it by hand. I take that back. There will be a situation where we have to do something similar to this, but I'm not going to make you compute the variance and standard deviation of a data set by hand. By the way, back in the olden days, like 20 years ago, when I taught statistics, this is all we had were those junky calculators. And so this is what we did. It took forever. It was horrible. So you have been saved from this by the wonders of Excel. You should be thankful. I know it's grumpy having to deal with Excel, but it's a really great tool. Okay, so 5.9. What in the world does this mean? Well, this means a couple of different things, but we're going to study 2 things that it means, 2 ways of looking at this. Here, I'm going to just switch over here so I can write them down. So one of them is called the empirical rule. Oh, here, I'll just here. What does the standard deviation mean. Sorry, it's kind of messy, but you get the picture. What does the standard deviation mean? There are two ways that we're going to describe what it means, and these are both mathematical theorems. One of them is called the empirical rule, and the other one is called Chebyshev's rule. And Chebyshev, I don't know how to spell it because he's Russian, and it seems like it's spelled differently everything. In fact, I'll bet you it's spelled differently on the PowerPoint than I just wrote down there. Doesn't matter. Okay, so just a brief explanation of why we have two different rules. The first rule, empirical rule, this is for roughly symmetric mound-shaped data. So because a lot of data that we look at looks sort of like this little piece of paper I gave you, it's surprising how much of the world fits this shape. Because of that, we have a special rule that only works when you have something that looks like this. Now this is actually a normal distribution. It's a Gaussian distribution. So this curve has a special name, but this is a stand-in for anything that is roughly symmetric and mound-shaped like this. So that's what the empirical rule is for, things that look like this. Chebyshev's rule, sometimes Chebyshev is spelled with a T at the beginning, just so you know, like Tchaikovsky. But anyway, Chebyshev's rule, that one is for everything else. It's for any distribution. Okay, so maybe without further ado, we should look at the empirical rules so that you understand why we care about standard deviation. Standard deviation will it will divide your data. You know, like quartiles? Quartiles divide your data into fourths. Standard deviation divides your data into very specific groupings as well. And we're going to put those groupings on this piece of paper in just a minute. And I hope that this piece of paper helps you. We'll see. I don't know, maybe it doesn't. If it doesn't, just throw it away. So let me get you the empirical rule first. Now, before I show you this, let me just caution you, don't write on this yet. I've got something very specific I'd like you to write on this piece of paper. So set this aside and write on whatever other paper you have or on your notebook or whatever. So here's what the empirical rule says. I know it looks really complicated, and actually, I don't even like this one. I'm going to make my own. Sorry, I don't like that. It's too complicated. Let's make a new one. So first off, we need to draw a roughly mound-shaped symmetric distribution, and here is how you do that. Let me just give you a couple of hints, and because it's hard for some reason to do this. So this has several features. One of those features is that it kind of curves outward like this on the sides, and then it has the mound in the middle. So here's what you want to do is you want to think of a 1950s girl's haircut. Okay, not 1990s, not 1980s, it's 1950s. So here's the 1950s is, right? It kind of goes out like Gidget, or maybe no one knows that. Okay, the 1990s is more like this, isn't it? I don't know. Yeah, and don't do this. I don't know what kind of haircut that is. But yeah, so it should kind of bow out at the edges, you know, like this sort of thing. Okay, so that's what we're going for, is something that kind of, it curves, so you've got this distinct curving up over the head, and then you have these sort of curving out towards the shoulders. Okay, so let's go back to this. I know this one actually is not the greatest. I'm going to erase it and try again. Let's try, try again. Erase, one more eraser, there. Let me try again. So I curve up, over, down, good enough, whatever. Okay, so once you have your normal curve, you can put markings on it to represent the standard deviations. So the mean is always in the middle, so this is going to be the mean, right there. Now for those of you who care, and I know some of you are more pedantic than others, so if you really care, The standard deviation is where you stop curving downward, getting steeper, and start curving upward. Mathematically, we call that a point of inflection, but you really don't need to know that. You don't have to be perfect with your markings. Just for those who are pedants, you can get it perfectly at that point there. So you can see how if you were skiing down the hill, it's getting steeper, 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 and then it gets shallower, shallower, shallower. So right there is about where the point of inflection is. And it should be about the same on either side. So I'm going to do that and that close enough. So you'll notice that this is the mean plus the standard deviation. And this is the mean minus the standard deviation. That's what the standard deviation does for you, is it sort of shows you where on this sort of mound shape you're going to find these. This probably should be over a little bit, doesn't matter. Now here's the beautiful thing about this, and here's how I'm different than my PowerPoint. You see all those percentages. I'll give you some simpler percentages. Those are way too complicated. So much simpler, 68%. So empirical rule just says that about 68% of a distribution will be between the standard deviations. Excuse me. By the way, standard deviations for height, 3 inches. So about 68% of us should be within 1 standard deviation of whatever the middle was. So if you're within 3 inches of the middle, you're kind of normal. Doesn't matter which side you're on. You're typical. Okay, well, what about the rest of us? Because I'm not within 3 inches unless I actually go with my true height and don't stand on my toes because I have shrunk in my old age. But anyway, in my younger self, if I go that same distance, so notice if I go about that same distance out, I get the mean plus 2 standard deviations. And down here, the mean minus 2 standard deviations. Don't worry, I'm making sure that the clock, that we don't, I know you want the answer to how to impress the ladies and girls. I know you want to know how to find that special guy. So we'll get there. But now, if you go 2 standard deviations, then this entire space here, so let me just do it like this. That is 95%. Roughly 95% of everyone is going to be within 2 standard deviations. So I'm guessing that almost everyone here was within 6 inches of the average. There might be 1 or 2 of you who were either 6 inches, more than 6 inches taller than average, or more than 6 inches shorter than average. But almost everyone is going to be within 6 inches of the average. That's what this says. 95% of us will be in that range. Finally, let's go one more. 3 standard deviations. So put a little mark right there. That's the mean plus, I'm sick of writing it like this. I'll do this. X plus 3 standard oops. I'm going to use the Greek letters. I can't mix them. So we'll use average. Okay, so that's another issue, but here, bear with me. Let me just write this down here. This is going to be the mean minus 3 standard deviations. Okay, so let me do a quick aside. Oh, keep going. Okay, so this Greek letter, that is the Greek letter mu. That's what a cat says. It is not what a cow says. This is mu. I don't know how to spell mu. There. Okay, but typically it's spelled like that. But it's supposed to sound like a cat, not like a cow. Not moo, it is mu. So, with that said, another thing I should say is how to write this. What you're doing is you're making a U, and you're putting little tails on either side to make it kind of look like an M. It's kind of like a cross between an M and a U. So when you see this, that's what it is. It's the Greek letter mu, and that is the population mean. Usually that tail is a little longer than the other one. Population mean. So that's the Greek letter mu. I know I've written this before, but I want to make sure that we get this. And the other one is this sigma. So that looks like an O with a little tail off the top. So that's the Greek letter sigma. This is the population standard deviation symbol that we use. So that is sigma. You might have heard the phrase 6 sigma. That's kind of what we're about to refer to with this empirical rule, but that's the population standard deviation. Okay, let's go back to the empirical rule, and then we'll use it. Don't worry. We're not going to give up before we use it. So if we go out 3 standard deviations, which, if you think about it, that means 3 down here and 3 up here, which is a total of 6 standard deviations, 6 sigma. Some people, these business people, really love that phrase for some reason. But anyway, that from here to here, let me see if I can do this, from there to there is 99.7% of everyone. Almost everyone. Just a very small. So here we would have people like, I don't know, LeBron James is out here, beyond 3 standard deviations. Manute Bol, if you remember that person from the 80s. Maybe you guys don't. And then down here, Spud Webb, another basketball player, but he was super short. So anyway, so 99.7%. There are just a very few people who fall outside that range. Whew. Okay, how are we going to use this? Well, here's how we're going to use it. Take that little piece here. Now we're going to use the piece of paper. So let me just draw this. Here's my piece of paper. In fact, I could do this up here, I suppose. Give me a sec. I think I can do this. Give me a sec. What if I use my camera? Camera. There it is. Yeah, look at that. It's like I've got a little document camera. Isn't that cool? Ooh, yeah. That's so useful. I don't know. Okay, so this may be a fail. You'll notice at the bottom here that I've got little markings. Whoa. Wait, I didn't want that. How do I get rid of myself? If I just do this. Okay, let's try again. Come on. Oh, here, I found it. Sorry, I got to remember gestures. I got to be careful. Okay, so you'll notice these little markings here. So the middle one is the mean, and then you can do the mean plus the standard deviation, the mean plus 2 standard deviations, and then out here the mean plus 3 standard deviations, and down here the mean minus the standard deviation, and here the mean minus 2 standard deviations, and mean minus 3 standard. I know there's not a line there. Okay, now what I'm going to do, and I don't know if this is useful or not to you, but I'll show you in a minute. What I've just done is I'm going to take this thing and I'm going to fold it on the lines. I'll show you here as best I can. There. Okay, so just so you can see I've got 2 creases there. I've got a crease at the mean, and I've got a crease at this, and I'm going to do another crease at the other standard deviation. I'll just do those for now. Okay. There we go. So now I've got those 3 creases. And so now the deal is that between those creases, so you have those creases there, that between them is 68%. So you got 68% of everyone will be in this middle section. That means that each of those little bands is 34%. See, this is 34%, that one's 34%. Okay, so give me a sec here. It'll be easier if I do it like this. 34%, 34%. Okay, so there it is. So there's my starting. Now we're going to do the same thing. We're going to move our way out 1 to the next band. So I'm going to put fold to the next chunk. Give me a second. There. And there. Okay. I'll show you what I've done. Okay, so you can see here, I've kind of folded it backwards, right at the 2nd standard deviation. And then, let's see, Now I'm going to have to do a little bit of math for us, but once I do the math, you don't have to do it ever again. So between the two standard deviations is 95%. But I've already got 68% here. So now I've got to do, like I said, I'll do this. I'm going to take one for the team here. So I've got 68%, 95 is the whole thing. That means that there is 29% in the two bands that, not in total 29%, because 68%, wait, did I do that wrong? I did it wrong. It's 27%, isn't it? Do I need a calculator? Let's see, 68 plus 27 is 95, right? Yes. So it's 27%. Sorry about that. I would have figured it out in a sec because I know what these numbers are supposed to be. So 27% has to be divided between those two bands. That means 13.5% in each one. So 13.5% in each of those bands. Whoops. So far so good. We're almost done. The last bit. So what's not accounted for? What's not accounted for is all the rest. And this is a little bit confusing, so I'm going to put two different numbers on here. I know it's going to be annoying. The first number is everything. So if you start at this line and you go all the way as far, like everyone, including the LeBron Jameses, I guess that would be this direction, all the super tall people, or all the super short people. If you include everyone, that would be half of all the remainder. Now there's 95% in the middle, and so that leaves us with 5% to go between here. Just a minute. I don't think you can see what I just wrote. And over here, 2.5%. There we go. I'm not quite done though. So just to bear in mind that those 2.5%, 2.5%, that includes everyone. Maybe I'll put a little arrow to indicate everyone all the way across. Okay, my arrow's terrible. You're probably doing a better job than me. Whew. One more thing, and then we're going to take a look at problems for just a few minutes, because I'm going to save the last 5 minutes to tell you how to impress people with your special dance moves. And then the last thing is these little tiny wedges. I'm going to just pick this up and put it up here. So those little wedges, remember that it's not 100% that go within 3 standard deviations. It's 99.7%. So that means that there's 0.3% that's unaccounted for within the, so I need to, let me see if I'll jot it down and I'll put it down there because I have to write really small to get it in that little wedge. So this is going to be 2.35%. Give me a sec here. And this is 2.35%. Ugh, that's terrible. Well, I was thinking I needed to make these a little bit bigger, but such is the way that this worked out. So there it is. So you can see my 2.35% is that little, that's the bit of the wedge that goes, that stops here. 2.5% is everyone all the way. Okay, so I'll let you take a minute to jot those down in case you didn't get them all. I can move this back and forth, but it's symmetric, so you've got the same thing on the left as you do on the right. And my thing is not working for some reason here. All right. There we go. That's what I want. Oh, now we're back to this. Okay. Let me get my, I need a couple of problems here. Example, here we go. Ignore that one, I don't like. Yeah, I don't like that either. Just looking for a good example. Okay, we'll use this one. We'll ignore the words, the Chebyshev thing. Oh, it's not showing up. I'll just have to advance. Yeah, here's Chebyshev's rule. Chebyshev's rule is, darn. Okay, I'll just make up my own problem. Chebyshev's rule is the same as this. It just is different numbers because you don't have this regular mound shape. I'll put it up here in a bit, but let's do an example. Let's take IQ scores. So IQ scores, the mean is depending on the test. So you probably heard about IQ, intelligence quotients, and depending on what test you use, the mean will be 100 usually. Standard deviation, sometimes 15, sometimes 20, depending on the test, which version of the IQ test you use. So let's use this. Let's say that this is the case. And I want to know how many people are between 115 and 130. Let's answer that question. So let me just show you how you're going to use this little piece of paper to answer that question. First things first, you make a normal curve as best you can, put 100 in the middle, mark this off. Here's 115, here's 130. So you mark it off using the standard deviation on the bottom. You can do the bottom as well if you want, but you don't have to. Next, you're going to mark this like that and say, hey, these are the people I'm interested in. I'm interested in those people that are between 115 and 130. Now we're going to consult this piece of paper here, and since I've already got it folded, what I'm going to do is I'm just going to fold the paper where I need to. Okay, it didn't quite work the way I'd hoped, but I'll just do this, and then you can see, there it is. There, let's see if that worked. Okay, it's so pitiful. It looks like something like a piece of garbage. Okay, there it is. But you can see, here, I'll stretch it out. Yeah, I think that's a fail. There. But you can see that the band, there it is, the band that I'm interested in is that 13.5%, and that's going to be my answer. So how many people, or what percentage? Percentage, I should have written that different. That's 13.5%. All right, let me do another one and see if you can answer this. How about this? What percent are between 70 and 115? All right, so what percent are between 70 and 115? I'll even fill this out for you. So take a minute, use your little piece of paper if it's helpful. I don't know if it is. Like I said, if it's not helpful, it kind of looks like garbage now. You can just put it in the garbage. All right, so let me do it on my piece of paper. This one hopefully will look a little bit better. Oh yeah, this is going to look better. So you can see I've shaded in red up there what I'm interested in. Now let me show you what I've done with my piece of paper. There it is. You can see that I'm interested in those three chunks. Now I just have to add these up. 34 plus 34 is 68, plus 13.5 is 78, 81.5%. So 81.5% will be the answer for that. So that's how you could use this to answer the questions on your homework regarding the empirical rule. This is just a little bit more refined version of the empirical rule. By the way, we have one more minute before I have to start the answers to the thing that I showed you at the beginning, and that is this, that Chebyshev's theorem, or Chebyshev's rule, says that if you don't have a normal distribution, or rather, if you don't have a mound-shaped symmetric distribution, you can still predict how much or how many people are in each of the ranges of standard deviation. It's just not quite as refined or good. And he has this formula, 1 minus k squared. So if you're going 2 standard deviations, then you would do 1 minus 1 over 2 squared. 2 squared is 4. So what Chebyshev says is that at least 3/4 of everybody is going to be between 2 standard deviations. And if you move out 3 standard deviations, at least 1 minus 1 over 3 squared, which is 8/9, or about 89% of everyone is within 3 standard deviations. So if you don't have a nice bell curve, then you're gonna have to use what's called Chebyshev's theorem. But it works the same way. I suppose you could make a paper, but the problem with making something like this for Chebyshev is that this is true for all sorts of weird distributions. They don't all have to be mound-shaped. So this one is good for mound-shaped distributions. Chebyshev is a little different. Okay, so answers. I know you're dying to know, so let's see. The statistics you can use. So first of all, what was it? Where should the women approach the dudes to catch their eye? And this is based on the Hungry Man survey, what I call the Hungry Man survey. Here's the reference. And they sampled 30 hungry men and 31 satiated men. And what they did was they showed them photographs of women in tight leotards and asked them to rate them as to their attractiveness. Now let's set aside the Title IX issues involved. And just let's look at the data, okay? Because it's really fascinating. You might wonder, where did they find these people? Well, these people, they would go to the cafeteria. And as the guys were going into the cafeteria, they'd say, "Are you hungry?" And they'd say, "Yes." "Are you really hungry?" And if they said, "Yes, I'm super hungry," they would say, "Let me just ask you a few questions." And then on the way out, "Are you satisfied? Have you eaten enough? Are you full?" That's those people. Now here's the interesting thing. They showed them 50 photographs, and these people rated the attractiveness of the women in the photographs. Now here's the data. I know it looks a little bit confusing, but the open dots are the average rating that the hungry men had, and the solid dots are the average rating that the satiated men have. So for example, for this particular photograph, hungry men said that's a 7. Satiated men said that's a 5. So you can see where I'm going with this. Now, just as a bonus, notice that they took the BMI of, I know, once again, it's a little bit sketchy, but they took the BMI of the women in the photographs, and if your BMI is between, say, 25 and 35, that's a sweet spot for catching the guys on the way into the cafeteria. Because notice there's a huge gap. The effect is not as great if you have a BMI of 20, and down here when your BMI is like, if you're really ripped, this isn't going to help you, I guess. Okay, but there it is. So on the way into the cafeteria, if you guessed that, you guessed right. Now, guys, how are you going to attract those women other than just being hungry? No, you don't want to be trapped by them, right? You want to attract them. So this is called the Dancing Man study. So just as questionable as the methodology was for the Hungry Man study, here they put guys in tight leotards, and they made computer-generated models of them dancing. I'll even show you the best and the worst rated dancers. But anyway, they tried to figure out what is it about the dancing that made women think that's a good dancer or an attractive person. And they said that the key measures were variability and amplitude of movements of the neck, trunk, and the speed of movements of the right knee. So right, not left knee, guys. The right knee, apparently, is where you want to focus your efforts, a la Elvis, I guess. Didn't Elvis do that thing? So I know you want to know, what did these guys look like when they danced? Well, let's see. I know I've got it here somewhere. Here it is. So let me just show you really quick. They're just short videos. This is what they showed the women in this study. So this is the worst rated. Wait, where is it? Give me a sec here. Open. Come on. Where is it? Should open it ahead of time, apparently. I've just got the circle of death. It's not going anywhere. Let me try again. Oh, here it is. Okay, just a minute. It's on the wrong screen. Hold on a minute. You'd think that I could get this straight. Okay, so this is the very worst rated dancer. I know, it's just a computer-generated model. So this is what I look like when I dance, by the way. Okay, now the best one. So guys, here's what you want to look like. This is the very best rated dancer in this study. Waiting. Where is it? Oh, yeah. I just want to point out the right knee. I mean, that's where it's at right there. Of course, now this study was done about 12 years ago, so things may have changed. Perhaps the arm is now the important part. And this is exactly what they showed. Well, theirs were probably higher quality. So don't say that you never learn anything useful in statistics. Guys, you can get your dance moves. Girls, you know where to get the guys. All right, stick around if you want to complain about your exam or if you have questions. Otherwise, we'll see you on Wednesday. I'm going to stop the recording. Stop it. It is